FastMCP3 introduces a server-level state management mechanism through composable lifespans, enabling shared data initialization and cleanup that persists across all client sessions. This pattern leverages asynchronous generators to establish a context that remains accessible throughout the server's operational lifetime. We're about to examine how a lifespan function initializes shared state and exposes it to tools via the context system, demonstrating the framework's approach to server-wide resource management. The code will reveal the interplay between lifespan context and tool execution, showcasing FastMCP's mechanism for maintaining state consistency across multiple tool invocations. From FastMCP, import FastMCP, context. From FastMCP, server, lifespan, import lifespan. At lifespan, async def app lifespan server. Hash initialize shared state. Data equals users, Alice, Bob. Yields data, data. MCP equals FastMCP my server. Lifespan equals app lifespan. At MCP, tool. Def list users text, context list SDR. Data equals CTX, lifespan context data. Return data, users. This code demonstrates FastMCP3's lifespan context feature for sharing server-wide state across tools. The @lifespan decorator defines an async generator that initializes shared data during server startup and yields a context dictionary containing that data. Here, @lifespan creates a data dictionary with a users list, which becomes accessible to all tools through CTX, lifespan context. The list users tool showcases how tools access this shared state. By retrieving the data dictionary from CTX, lifespan context, it can return the user list without maintaining its own copy. This pattern is particularly useful for configuration, cached data, or any state that should persist across all client sessions, but only be initialized once at server startup. The approach provides several advantages. It ensures data consistency across tools, eliminates redundant initialization, and maintains clean separation between server-level and session-level state. The try finally structure in the lifespan ensures proper cleanup, though this example doesn't demonstrate teardown logic. This pattern is ideal for read-heavy shared data, while write operations would require additional synchronization mechanisms not shown here. Let's break it down. From FastMCP, import FastMCP, context. Imports the FastMCP class and context class from the FastMCP module, providing the foundation for creating MCP servers and accessing session context capabilities. From FastMCP, server, lifespan, import lifespan. Imports the lifespan object from the FastMCP, server, lifespan module, which provides server-level setup and teardown functionality that runs once when the server starts and once when it stops. At lifespan, async def app lifespan server. Defines an asynchronous lifespan handler function named @lifespan that will be called during server startup and shutdown, receiving the server instance as a parameter. The @lifespan decorator marks this function as a FastMCP3 lifespan handler, which executes exactly once when the server starts and once when it stops, regardless of client connections. Hash initialize shared state. Data equals users, Alice, Bob. Initializes a dictionary variable named data containing a single key, users, mapped to a list with 2 string values, Alice and Bob. This creates a simple in-memory data structure that stores a collection of user identifiers, establishing shared state that can be accessed or modified elsewhere in the code. Yields data, data. Yields a dictionary containing the data variable under the key data. This is a generator expression that returns a single dictionary object when iterated over, commonly used in Python to return structured data from functions or coroutines. The yielded value will be a dictionary with one key-value pair, where the key is the string data, and the value is whatever the variable data contains at that point in execution.
MCP equals FastMCP my server. Lifespan equals app lifespan.
Creates a FastMCP server instance named my server with a lifespan configuration specified by app lifespan. The server identifier, my server, will appear in MCP protocol handshakes for client identification, while app lifespan defines startup and shutdown behavior that executes once when the server starts and stops, independent of client connections.
At MCP, tool. Def list users text, context list SDR.
Defines a FastMCP tool function named list users that takes a context object and returns a list of strings. The @MCP tool decorator registers this function as an MCP tool, automatically using the function name as the tool name and generating input-output schemas based on the type annotations.
Data equals CTX, lifespan context data.
Retrieves the value associated with the key data from the lifespan context dictionary stored in the CTX object. This accesses server-level data that was set during the lifespan initialization phase and persists for the entire server runtime. The variable data now holds whatever value was stored under that key in the lifespan context.
Return data, users.
Returns the value associated with the user's key from the dictionary stored in the variable data. This assumes data is a dictionary-like object containing a user's key, and the returned value could be any data type list, string, object, etc. depending on what's stored under that key. FastMCP3's lifespan context feature enables server-wide state sharing through a clean, composable pattern. The @lifespan decorator marks an async generator that initializes shared data during server startup, yielding a context dictionary that persists for the server's lifetime. In this case, app lifespan creates a simple user list and exposes it via yield, making it accessible to all tools through CTX, lifespan context. The list users tool demonstrates how tools consume this shared state without maintaining their own copies. By accessing CTX, lifespan context data, it retrieves the server-level user list, ensuring consistency across all tool invocations. This pattern eliminates redundant initialization and maintains clear separation between server-level and session-level state. The key insight here is the seamless integration between lifespan initialization and tool execution. The async generator pattern ensures proper setup and teardown, while the context system provides a unified interface for tools to access shared resources. This approach is particularly effective for read-heavy shared data, though write operations would require additional synchronization not shown in this example.
The lifespan whispers its data to the tool, while the server hums a lullaby to its own shutdown.